Hello and welcome back to Calculus 3. We have section 11.7 on motion in space. We're going to take a look at 2D and 3D motion. And everything will be based off of the path function, the trajectory, which is our good old vector r. So we have the 3D system. We'll take the right hand one, x, y, z. We're going to put some trajectory there, which is the path. And this is, well, yeah, trajectory. And we're going to call it r. Now we know that vector r is a vector valued function in time in terms of t, and we can find a position, any position, by computing vector r at some time t0. So vector r computed at some time t0 will give us the position of that vector. And then we can also calculate the velocity at t0, which would be tangential. That's also a vector. And then we'll see that there is also some kind of acceleration. Well, now that's crowding the picture. So let's leave it at this. So we have position, we have the velocity, the magnitude of the velocity is speed. So these are the concepts. So r of t will give us the path function. Velocity of t is the velocity function. It's a vector valued function, but it's less letters this way. A of t is acceleration function, and if the object is in a free fall, it will be given as the gravity will be constant, right? And it will be z. You can put negative z, positive z, whatever way you want to put that sign. Just make sure you be consistent with everything else. So now all of the Calc1 stuff still works the same way. So you can go and you can get velocity as a derivative of the position, and get acceleration as the derivative of velocity, or the second derivative of position. You can get the velocity also as the integral of acceleration. These are all vectors. I'm just lazy to, well, I shouldn't be, but here, we'll fix that. And we can also get the path function r as the integral of the velocity. So everything that we learned, now we seen the vector valued function last time, and we know that we can integrate and differentiate each one of these components in a vector separately. So technically we are working on independent calculus 1, either derivatives or integrals. They're all independent. And then we can find a vector c, right, the constant vector, if we have some kind of initial position. So that was an example that we did last time. So we look, well, let's pick an example so it makes sense. Then we'll take a look at motion, and then we're done. All right, so what does this say? Let's take a look at the slinky. Remember the slinky? It was a slinky that was connected into a donut. So this is problem 16. They're looking for the velocity, they're looking for the acceleration, and they're giving us r at 3 sine t, 5 cosine t, so this is elliptical slinky, and 4 sine t. From 0 to 2 pi. So now what I have here, the velocity and acceleration. So we'll find the derivative, well, let's write the velocity is the derivative of the position function, so I am supposed to take the derivative of 3 sine t, 5 cosine t, and 4 sine t. So velocity as a function of time will be given as 3 cosine t negative 5 sine t and 4 cosine t. And now acceleration is the derivative of velocity. So we have to take one more derivative, and that would give us negative 3 sine t negative 5 cosine t and negative 4 sine t, and that will be it. So they were looking for these two functions here. Now if you need to figure out where is the object, where how fast it's moving, and what is its acceleration, you will have to provide a time. So let's say you provide time at pi over 4 seconds. You will plug that in for each t, and you will compute the location and the velocity and the acceleration. Speed is the absolute value of velocity. They did not ask for that, but I'll just say over here speed equals the absolute value of velocity vector. So you can find that as well. All right, so that's motion given any vector r, right, which is the path function. Now what we are interested in is the two-dimensional motion in gravitational field. We want to see what happens as you throw something, what happens. Now anytime you throw something, it's technically 2D motion, because when you throw it, it occupies a plane unless you manage to throw the curveball or something that has the parabolic and the curve. But generally, let's do the experiment. You don't have to worry, because I am not aiming at you. If I would, there would be no way for you to hide. It doesn't matter. Yeah. So this is going to have the parabolic motion. But see, we are in a 3D classroom, right? And when we are in a 3D classroom, that's a 3D space. This marker is still going, because I'm not going to throw a curveball marker. That's why you don't have to move. Don't worry about it. It's going to go there. It is going to occupy a plane, right? And in that plane, all you have is just the parabolic motion, right? Yeah. So we have this type of a motion, which is the height y in respect to time t. And you can see that it's a parabola that opens downwards. Now, in physics, you learned the equation of this, but you did a much better job in calculus, where when you see in that your acceleration starts at negative g, right? Negative gravity, because we like to put the positive motion up, right? So as soon as you do something like that, then this acceleration is actually change of velocity in time, when you do the differential equation here by separating variables, you have that dv equals negative g dt. And when you integrate both sides, you get that the velocity is equal to negative gt plus some initial velocity. That's plus c in the integral, but then we call that initial velocity. And you have seen this formula in your physics class as maybe velocity final is equal to velocity initial plus acceleration times time. And now we put negative g for acceleration because it's a free fall. So we have the equation for velocity, and then you go and you say that velocity is change of position in time. In our case, that would be r, and you do the same thing, getting the equation for height, which is negative 1/2 gt squared. So let me just write here differential equation. This would be ds is equal to velocity dt, and then you integrate both sides. So that's a differential equation. You create, you make it into different separate variables, right? And then you just do this. So now gt plus v0t plus some y0 initial height. So the three equations that are important are that for the free fall, when you drop something or throw something, the vertical component will be of the velocity will deal with the gravitation as the acceleration. Velocity will depend on the gravity as well as how fast you throw something. And finally, the height will depend on initial velocity and initial speed. Now, these formulas that you have seen 15,000 times so far in multiple courses, we are going to just put in a vector. And we are going to keep these in a vector notation. So now motion in R2. R2, you know, that's the 2D space. And we are just going to give these as a vector. So I have that acceleration vector. This one is not mentioned in your textbook, but such is life. There is a zero gravitational pull, acceleration in x direction, but then there is negative g in y direction. The velocity vector is going to be given as u0 and negative gt plus v0. I'll explain these. And then r vector is going to be given as u0 t plus x0 comma negative 1/2 gt squared plus v0 t plus y0. This is the standard stuff. Now, these are the equations that are going to be boxed. This is what we actually use for 2D free fall. And I just want to point some arrows and put some acceleration. So this over here is x-axis position. And you see that it depends on x0 initial position. And then u0 is velocity in x direction. So you see over here that the x direction of motion velocity is given as a u0. And you have the initial position, and then you change that position according to the velocity, which is the reason why you were able to come here to the classroom. On the other side, this one over here is the y-axis position, so in the y direction, and you have the gravity term, which is the one that pulls everything down. You have the velocity, initial velocity depends on how hard you throw objects, and then you have the height from which you throw objects. That is all important, right? This is the reason why generally basketball players are very tall, right? Because those hoops are high up, right? That's it. So parabolic motion works better the taller you are. So now, when you have the word problem, you just need to pick the values and plug them into the equation. As you can see, I really hope you haven't learned anything new. You just redefine the terms that you already know and put them into a vector. Technically, if you integrate 0, you will have 0 plus a constant. When you integrate a constant, you pick up t plus another constant. So this is all stuff that you have seen in your previous calculus courses, and if you took analytical physics, this is better. So they give you actually example in the textbook, example 4, a flight of a baseball. They say that the velocity 0 is given as 80. That means that the baseball was thrown at 80 root 2 meters per second or feet per second. So 80 root 2 feet per second at 45 degrees, which gives you 80 on x and y components. And then they are wondering if it can clear a fence that it's 20 feet, 380 feet from the home plate. So you're looking for the height for that particular, right? Because you want to know where the ball is at all times. Let's see if we can find. I mean, obviously you can read this example. So oh yeah, I forgot that they give you these formulas as well. There are these formulas. I'll just call them physics. Time of flight. So time of flight is 2v0 sine at which you are thrown divided by the gravity g. Range, how far it gets, will be, again, depending on the speed and sine. We're not going to derive these formulas. And max height. Now, you don't really need to memorize these. There is a cool way, and that's what we're going to do now, to figure out the maximum height without memorizing the formula. I mean, if you love memorizing formulas, please, by all means. Right? There is a cool way to deal with the max height. Let's see if we can find an example in the. All right, so figure out everything for a baseball thrown horizontally from a height of 10 feet above. Oh, well, that's already maximum height. It's horizontal, and throw something horizontal, it's just going to start going down. So that's your max height. Maybe this is. Yeah, I don't like problem 40 because we can't do maximum height. What can we do with the max height? Okay, 38 we can do with the maximum height. So a golf ball has initial position x0, y0 as 0, 0. When it hit at the angle alpha of 30 degrees with the initial speed of 150 feet per second. I'll just say get all. All right. So first, what do we have? Well, if I have initial velocity, right, given as a number and the angle at 30 degrees, we can figure out x and the y components of that. So, you know, just draw the thing. You know it's going to be parabolic motion. If we're starting at 0, 0, right there. Oh, it's launched at the 30 degrees, so it should look like something like this. Here's your vector at 30 degrees over here. And we have it at 150 feet per second. And then it's going to hit and fall somewhere x distance away. So I can actually use these numbers in these formulas, figure out the time of flight, figure out how far it goes, and figure out what the max height is. But that kind of kill all of our, you know, interesting calculations. So let's just develop all of these formulas. So first off, I see that my if I draw a triangle like this, right, and this is 30 degrees, and I know this is 150, I can figure out velocity, initial velocity u0, right, which is the x initial velocity, and the v0, which is this velocity on the y. So u0 is the initial velocity given, which is our 150, times the cosine of 30 degrees. So that's going to be 150 cosine 30 degrees, which is 150 root 3 over 2. And that's going to be some decimals. v0, which is our vector y component, is going to be initial velocity given by the sine of 30 degrees, which is 150 sine of 30 degrees, which is 150 times 1/2, and that's 75. So now let's just see what's 75 times root 3. $129.9. Should have called it 130, but nah. All right. So now we have these, and I can place these into a vector that we. So now I know that my velocity vector in terms of time was given as u0t plus x0, comma, and then we have and then we have v0, well, negative gt plus v0. And we have these values. So velocity vector is given as u0 times t. That's going to be 129.9 times t. And then negative 32.2t plus another 0 because, oh no, sorry, plus 75. Plus 75. There we go. Wait, hold on. There's no plus x0 here. It's just, these are velocities. That's it. Sorry. These are velocities. So we just have 129.9. Yeah, good. Okay. So now r of t will be 129.9 t. There we go. And this one is negative 1/2, so this is going to be negative 16.1 t squared plus 75t. And then plus 0 because of for y0. Both of these have plus 0. I'm not writing them. These are your plus 0 and plus 0 for initial velocity on x and y. So now I have my equations, and from here we can figure things out. For instance, I can go take this equation here, right, and use it to figure out max height, because maximum height is going to be when your vertical component of the velocity is equal to 0. Anytime you throw something, it's going to go up and then it's going to fall down because of gravity. So when you when it changes the direction from going up to going down, it stops, and that happens at the max. So if we take that one, negative 32.2 t plus 75, and we set it equal to 0, you will find the maximum height. Well, you will find the time at which maximum height occurs. So the time over here is negative 75 divided by negative 32.2, and that's going to give us the seconds. So 2.3 seconds is when the maximum height occurs, and then you will feed that into the bottom equation to find the max height. So y max is going to be negative 16.1 times 2.3 squared plus 75 times 2.3, and this calculation will give us what we need. So we have negative 16.1 times 2.3 squared plus 75 times 2.3, 87.3 feet. So max height is 87.3 feet. We can also, well, acceleration is clearly 0 and then negative g, right? Because, yeah, whatever. Let's write that. Acceleration is 0 in the x direction, there is no acceleration, and in the y is just negative g, so 0 and negative 32.2 feet per second, or feet per second squared, whatever you want to call it. So these are the calculations that you can do. Now, since you have the position vector being this one over here, right? Position vector, given any time, you can figure out the height, the x, so which would be the range, and the height. You can figure out the range as well easily, because your height needs to be 0, right? So when you set this one equal to 0, you figure out the range, because you will figure out the time at which, and then you use that time in here to figure out how far it went. So here, green, range, without using those physics formulas, you figure out the 16.1 t squared plus 75 t equal to 0, because, right? So you see that the first time is 0 for this solution, so the other time that you get would be this one. Range is how far it went. So when I figure out how long it took to hit the ground on the other end, I'll know how long that would be the time of flight as well. So with that one, we take care of the time of flight and how far it goes. So as you can see, we don't really need to memorize these formulas. There is a way to reason with this and solve it quickly. So we factor out t, and we have negative 16.1 t plus 75 equal to 0. T equals 0, we know that's the first solution, and the second solution is negative 75 divided by negative 16.1. So negative 75, so 75 divided by 16.1 is 4.7 seconds. And now we plug that in here to see how far it goes. So range is going to be 129.9 times 4.7 seconds. To get 610.5 feet. So that's how far it goes. If you took rudimentary physics, all of these formulas were there, and you might have to memorize the, today's standard is you can bring one sheet of paper with the formulas of physics. There's just no point for physics courses anymore. They should just scrap the whole thing. Students bring the formulas in. I've seen it thousands of times because I teach every day and I see students making those formulas. Oh, our professor said that we can bring 1 page of formulas to the physics. Like, why do you go to class? And why do you have exam? Like, what are you learning in that class? And also, all of the labs are garbage because everything is computer simulation. So you don't drop things, measure with a stopwatch, or measure the distance. You do nothing. I have no clue why physics courses exist. They should just scrap the whole thing. There's no point. Nothing. Nothing. Just complete waste of time. 5 hours a week wasted on nothing. There's just, I don't know why you get up. If the physics is the only course you're taking and you're not working, just don't leave the bed ever. Just stay there and just watch Netflix all day, because it's the same thing like going to the physics class. No reason, right? So there you go. You don't have to memorize the formulas. There is a common sense way to get this. All right? Done deal. So that's our motion in 2D, right? And now for 3D motion, the stuff gets a little bit more complicated. But again, the only thing that you have to worry about the 3D motion is where is the plane, right? First off, we took care of the 3D motion at the beginning, right? This is this over here. This is what I wrote. This is any dimensional motion. These vectors can be any dimension. You want to see the way the fifth dimension motion works? There you go. You will just have 5 of those vector components, x, y, z, w, and whatever your fifth one is. You will just have the 5-dimensional vectors. You integrate and differentiate each one the same way. Now, what is the interesting part about 3D motion? See, the 3D motion, I don't have another marker, so you're lucky. Because for me, I mean, clearly, if I'm throwing from here, I threw the marker. So this is not a straight shot. This is about 7 degrees this way. If I adjust exactly 26.1 degrees, right, that will be it. That will be directed right there. So all it does is shifts the plane. Now, if you go and say, oh, it's a curveball. What is a curveball? Well, curveball is going to be a parabolic in a parametric equations. X and Y is going to be parabolic, and then there is a curve, right? So bring in some sine or cosine on a direction as well, right? So the only issue for the 3D motion is to actually figure out the trajectory. Those now they're given to you, right? So the 3D motion problems are actually much easier and faster than the one that we did for the free fall, because for the free fall you should know some of the basic rudimentary physics equations to be able to do these things, right? And a lot of calculations. Now, if I give you the R, you see over here you were given the velocity, and when you're given the velocity, you have to go on and figure out your position function. For the 3D motion, we give you the position function, and then you just differentiate twice for the other two, and then everything goes the same. So for motion in 3D, you have your vector r of t, that is giving you the position, so that's x of t, y of t, and g of t, z of t. So we have our x, y, z of t, and then from there your velocity would be the derivatives of these. And your acceleration would be the second derivative of each one of those. Again, you should be able to take some calculus 1 derivatives to work with that. And that's it. So, hope you're not disappointed. Motion in space, 2D, 3D, or any D. Let's take a short break, and then next lecture.